So I'm analyzing groundwater flow in Meadows using a relatively new method called the self-potential method. And the project was focused at the Boulder Creek Critical Zone Observatory right here in Boulder, Colorado. And I was working with the Colorado School of Mines. Okay, let's begin. Okay, so this summer we had three main objectives to this project. And the first and probably most important goal was to measure groundwater flow using the self-potential method, and we wanted to measure groundwater flow in the shallow subsurface. So secondly, we wanted to measure the patterns of groundwater flow in Meadows simply because they are a less explored location, and usually when you think about people measuring for climate change, no one focuses on Meadows, so we focused on it. And lastly, we wanted to create diagrams of flow to see how the groundwater can change in the future due to climate change. And here's a picture of the Gordon Gulch watershed in May 2015, and it's just a meadow. It wasn't the meadow we used, but it's a meadow. Okay, so typically, groundwater is analyzed through the installation of groundwater monitoring wells, and here you can see an example of that. This is a groundwater monitoring well installed by the USGS in Connecticut. And now, although groundwater wells are an effective method of measuring flow in one location, they only provide information in one point. So that brings us to the self-potential method and what it is. So the self-potential method is a geophysical method that works by measuring the small voltage that occurs when water passes through the sand and soil in the ground. And when water passes through the ground, it drags along a very, very small charge. And we can measure these small charges and use them to understand the groundwater flow in the area. Now, although this method isn't widely used by the hydrology community, it's an effective way to measure the spatial hydraulic flow, direction, and patterns in a wide area. In order to measure the potentials in the ground, we use a voltmeter, a wire, and 2 electrodes. Very simple compared to what people have to use to install a groundwater monitoring well. And on the top figure, you can see that we have a base electrode connected to a wire, connected to a voltmeter, connected to another electrode. And that's pretty much all we use when we went out in the field. And the bottom figure here shows a groundwater scenario in which self-potential is collected. It's just a scenario. Now, all self-potential measurements are made relative to a single base electrode, which is right here. And we positioned this electrode about 25 meters away from our meadow, which was our sampling area. Now, to measure self-potentials in the ground, we buried an electrode about 3 to 4 inches into the ground using a bulb digger, which worked in our case as well. And we recorded 3 voltage measurements and took the average. And in this scenario, you can see that water is flowing down the meadow, down the slope. So in terms of self-potential, the more flow you have, the more positive the self-potential measurements will be. Thank you. Okay, this has been a problem. All right, microphone. Sorry about that, friends. Okay, so, the more flow you have, the more positive the self-potential values will be. And the less flow you have, it's not on. Okay. Okay. All right, continuing. All right, so the more flow you have, the more positive the self-potential values will be, and the less flow you have, the more negative. So in this case, the self-potential values will be moving in a positive direction. They'll be going more positive. And when I say self-potential, I mean voltage in millivolts. Okay, so now that you have a brief understanding of what self-potential is, we can dive into what I actually did this summer. So here's a map of the Gordon Gulch watershed. It's at the Boulder Creek Critical Zone Observatory in Colorado, also known as the CZO. And the CZO hosts several research projects, the same as you saw with Stacy, which is why I'm right after her. Okay, so using QGIS, we were able to map out a series of meadows in the upper basin. And we went out into the field and we mapped most of the meadows, and we chose one meadow based on the feasibility to collect self-potential values and the closeness to trail, since we have to carry out all our equipment. And the location of the meadow is somewhere in the yellow box here. So during the month of May and June, we went out into the field 3 times. So like I said, we went out in May once to look at the meadows and choose a location, and we went out once in the beginning of June and once in the end of June. We used a handheld Trimble GPS device to map the coordinates of the meadow so we can go back there, and we also collected self-potential values at one meadow. So after, we exported our data into an Excel sheet and analyzed it on QGIS and MATLAB to create diagrams of flow. Okay, so here's a figure of the setup we used when we went out into the meadow. And we used 2 to 3 measuring tapes to create a grid-like formation here. And our grid was roughly 40 to 45 meters long with 5 meters spacing in between. And we labeled our points numerically and alphabetically. So here would be A0, A5, A10, and so on. And the blue line delineates Boulder Creek, and it's moving from the top of the figure to the bottom of the figure. Okay. So after spending some time in the field, we went back into the computer lab and plotted some of our data. Also, we collected self-potential values at each point. I think I forgot to mention that, as well as the GPS coordinates. Okay, so this is a figure showing the self-potential values collected on June 10th. And the lighter blues here represent more negative voltages, and the darker represents a more positive. Like I said in the beginning, more positive voltage means more flow. So if we take a look at the pattern seen on the grid, we can see that the voltages move from a negative to a positive direction as it's moving toward the stream. So there's more flow in this general area, which is near the stream. And there's also a trend moving horizontally. Okay. And here's the same data plotted on MATLAB, and it shows the exact same trends as the last figure. However, plotting our self-potential values on MATLAB allows us to see a slope of the area and how fast water is flowing. And it's very similar to a topographic map in the sense that the closer together the contour lines are, the faster the flow and the steeper the area. And the upper arrow here shows where water is flowing at a faster pace, and the lower arrow shows where it's moving slightly slower. Okay, so we went out again on June 24th, but this time things were different, and we have some things going on. So one thing to note is that when we went out this time into the field to our meadow, there was a significant change in the vegetation. So there were increased vegetation growth, there were flowers everywhere, it was buggy, it was kind of hard, but we did collect self-potential measurements. And also something to notice is that the overall voltages here are more negative compared to the last one. In the last data set, we noticed that there was a range from negative 8.7 to about 12.8. And in this one, the millivolts were negative 27 to about positive 4, which is significantly more negative. But we can also see a slight trend showing more positive values closer to the stream. Okay. So again, similar to the last figure, this is a contour map of the self-potential values collected on June 24th. The contour lines are less close together in this graph compared to the last one, but we do see that there are more positive values closer to the stream area. So why might we see a shift in self-potential during these 2 dates? And in order to figure this out, my mentors and I created a list of things that might have influenced a change. So we came up with these 3: precipitation, change in vegetation, and the possibility of error. So based on the monthly climate data from NOAA, we found that there was a spike in rainfall in the beginning of June. So here, the 2 stars here represent the days we went out in the field. And like I said, you can see that rainfall increased dramatically. And I think you guys remember it was when Colorado was starting to look like Seattle. It was very wet. It was awful. So we went out and during one of these very high rainfall days, and we also went out on the 24th when you can see a significant decline in rainfall. So that could also pose an explanation for the change. And also, based on the negative patterns found on the 24th, we can also hypothesize that the shift in self-potential values can indicate that the shallow groundwater was being absorbed by the massive vegetation growth that occurred, because this time there was a significant change, and that could definitely be it. So it's always important to acknowledge the possibility of error. When we went out into the field the first time, my graduate mentor, Emily Voytek, collected self-potential values, and the second time I collected self-potential values, so there could have been a method shift, maybe. So it's always a possibility. So overall, this project showed that the self-potential method is in fact a successful method in measuring the patterns of spatial variation in shallow groundwater flow. And by proving this is an effective method, we can open a whole new world of understanding what goes on in the subsurface. Like I said in the beginning of the talk, typically groundwater is measured by groundwater monitoring wells, and they only measure a single location. But self-potential can measure an entire grid, which is great. So a shift in groundwater between June 10th and June 24th indicate that immediate weather influences the shallow groundwater flow in Meadows. And seeing that only a small period of unusual precipitation can affect groundwater flow so heavily, we can use self-potential as a method to examine the variability of hydraulic flow due to the expected climate change in the future. Also, meadows exist in a fragile environment and therefore are more likely to be impacted by climate change. In the future, we could definitely use more self-potential surveys. This time we only went out 2 times, well 3 times, but 2 times collecting data, and we can use a lot more surveys just to compare it. And it might also be helpful to conduct an electrical resistivity survey in order to understand the electrical properties of the ground and as well as the stratigraphy beneath the meadows. Okay, and just a couple of acknowledgements. I'd like to thank the Boulder Creek Critical Zone Observatory for the maps and letting us use the area, NOAA for the climate data, Emily Voytek, my graduate mentor, Kamini, Singha, my research mentor, Holly Barnard, my communications mentor, Recess, and of course, NSF. Questions?
Okay. Thanks, Annie. Oh, we have some questions. Okay.
Hi.
Hey,
okay.
So based on your precipitation graph,
Yes.
it seems that the precipitation is affecting, or likely affecting your results. Wondering how are you able to pull out the soil moisture from the groundwater stuff? Because aren't you just kind of focusing on the groundwater?
We're just focusing on the shallow groundwater. So it's likely that precipitation would influence the groundwater flow because we're just looking about 3 to 4 inches beneath the soil.
So when you say shallow groundwater, you just mean soil moisture? Yeah.
I don't actually know. Perhaps. I can get back to you on that.
Okay, no worries. Thank you.
Yeah.
I was just kind of curious if you think that soil temperature might play a role in this as well too, or just the expansion and contraction of soil causing.
Yeah, we definitely did think about testing for the temperature as well, but this time we were just testing out the method in the beginning. But looking at temperature is definitely something that people have done in the past, and I mean that could be explored in the future with meadows. So, yeah.
No more questions? All right. Okay. Thanks, Annie.
Thank you.